Hello everyone. So today I will be presenting regarding the topic called path connected sets. Okay, so it is an interesting topic from analysis. Okay, so in analysis, usually you want to understand and discover the structure or the properties of a set. Okay, so this would lead to the concept of connectedness, which studies whether a set stays as a piece. Okay, so this connectedness is actually a topological property of set. Okay, so today we will be studying a stronger and more visual version, which is called path connectedness. Okay, so it is more intuitive because path is a thing we can think of in the brain. Okay, while connectedness is too abstract, I would say. Okay, so this path connectedness idea, which can help us extend results like the intermediate value theorem to higher dimensions, to Rn, I would say. Okay, so let's have a look at this first definition, which is the definition of path connectedness. Okay, so we would say that a set S, which is a subset of Rn, is path connected if for all u and v in S, there exists a continuous function gamma defined on the interval 0 to 1 to S such that gamma 0 is equals to u and gamma 1 is equals to v. Okay, so from the diagram, we can see that uh, this path connected sets, we can draw a path connecting 2 points without leaving the set. Okay, while uh, for this disconnected set, we can say, although we draw a path connecting these 2 points, but the path somehow they leave the set at the middle. Okay, so in order to call the set path connected, we require the path to stay within the set at all times. Okay, so let's have a look at the second definition, which is the definition of convex set. Okay, so we say that the set S is convex if for all uv in S and T between 0 to 1, the point 1 minus Tu plus Tv is also lies in S. Okay, so as you can see from the picture, if we construct a straight line connecting xy, where xy can be any 2 points in the set, then this straight line this straight line connecting xy, they never leave the set. Okay, so why I would say straight line in this um, manner, because 1 minus Tu plus Tv is actually a like classical parametrization of a straight line in the higher dimensions. Okay, so actually we can visualize it as a straight line. Okay, so for non-convex set, if we connect these two connect these 2 points xy, we would see that a small portion of the line has already left the set. So this set is not convex. Okay, so in order to call the set convex, we require the line connecting xy, they also stay within the set. Okay, okay, so let's see the first theorem. Okay, so if the set S is convex, then it is path connected. Okay, so this theorem is like I would say connection between convexity and path connectedness. Okay, so for the theorems we will be proving next, the idea is to construct a path connecting two arbitrary points in the set. Okay, so in order to prove path connectedness. Okay, the idea is very simple. So let's see the proof. Okay, so we first let uv be in S. Okay, so since S is convex, for all t in the interval 0 to 1, the 1 minus Tu plus Tv is also in S. Okay, so it's natural for us to define the function gamma t, which is equals to 1 minus Tu plus Tv. Okay, so since we know that the components of the function gamma is all continuous because it is a polynomial, okay, the components are all polynomials, then we know gamma is a continuous function from the interval 0, 1 to S. Okay, and then if we further check out, we see that gamma 0 is equals to U and gamma 1 is equals to V. Okay, so we know gamma is a path in S from U to V. Okay, so since we have constructed the path gamma, we know S is path connected. Okay, so let's have a look at the second theorem. So the importance of this theorem is that continuity preserves the path connectedness. Okay, so it is actually interesting to relate these two important concepts of analysis together. Okay, so uh, if the subset of Rn D is path connected and F, which is defined on D to Rm, is continuous, then Fd is path connected. Okay, so as usual, we would like to construct a path. Okay, so let V1, V2 be in Fd. So because F is a function, then it must have a pre-image. Okay, so there exists U1 and U2 in D with FU1 equals to V1 and FU2 equals to V2. Okay. So since D is path connected, there exists a function gamma defined on 0, 1 to D with gamma 0 equals to U1 and gamma 1 equals to U2. Okay, so note that the gamma, because gamma is a path, so we know immediately that gamma is continuous. Okay, continuous on 0, 1. Okay, so let's define alpha be the composition of F and gamma. Okay, then we know that alpha is continuous, and because F and gamma are both continuous functions, so the composition of continuous function is automatically continuous. Okay, and then we know that this alpha is a path connecting V1 and V2. Okay, so we know that FD is path connected. Okay, so let's extend the concept of intermediate value theorem to a higher dimension. Okay, so if D, which is a subset of Rn, is path connected and F defined on D to R is continuous, then FD is an interval. So you like to prove that FD is an interval, which means that if we pick simply 2 points on R, we need to prove that every point between these two uh, between these two numbers are included in the set. Okay, so then we can show that the set is an interval. Okay, so we first let AB be an element of D, then we let FA equals to R and FB equals to S. Okay, so since D is path connected, then it automatically follows that there exists a continuous path gamma defined on 0, 1 to D, such that gamma 0 is equals to A and gamma 1 equals to B. Okay, so let's define H be the composition of F and gamma. Okay, so it's a usual technique we use. Okay, and since both F and gamma are continuous, so is H. Okay, then we can self-verify that H0 is equals to FA equals to R and H1 is equals to FB equals to S. Okay, so since H is the function defined from the subset of R to R, then we can use the intermediate value theorem from single variable calculus. Okay, so by the IVT, we know that for any t between R and S, there exists C, which is between 0 and 1, such that HC is equals to T. Okay, so since H is F composite Y, F composite gamma, we know that T equals to F gamma C, which is a element of FD. Okay, so since T can be any number between R and S, so we know that FD, it can contains every real number between R and S. So we know that FD is an interval. Okay, so let's have a look at additional lemmas and theorems. So if A, B are path connected and A intersect B is not empty, then A union B is path connected. Okay, so S is path connected if and only if S is an interval. Okay, and also if D is path connected and F defined on D to Rm is continuous, then the graph of F denoted as GF is path connected also. Okay, so in conclusion, we can see that path connectedness between means that we can move from one point to another within the set without having to jump out of the set. Okay, so it means that we can always stay in the set without without moving up. Okay, so from the previous, we know that all convex sets are path connected, and path connectedness is preserved under continuous mappings. Okay, so this path connectedness is actually very powerful, so that we can extend classical theorems like the IVT and also the extreme value theorem to higher dimensions. Okay, so thank you for listening to us. Okay, listening to me, and this is the reference I use. Okay, so thank you very much. Bye bye.